Okay, we're recording. Give people one more minute to filter in. Okay. Yeah, people are. It's after lunch, you know. You have to let the people.
I realized that only after having agreed to chair the session.
But you're just chairing this one talk, right?
Yes, for tutorials, I think it will be pretty much.
Yeah.
I hope. I will tell you when it's like 5 minutes to go or 10 minutes to go. Do you want any signal?
Yeah, sure.
10 minutes and 5 minutes then. And then when you are out of room. Yep.
Well, I'll be checking my watch. Just tell me when there's like 5 minutes left.
So at 2:25.
But the weird thing is my phone is always in the edge zone. My computer is. This computer's network card just like I never tried it. No, you're.
Okay, let's get started.
Everyone.
It's from an institution.
Everyone, welcome back to the afternoon session. Our next speaker is Owen Lynch that will talk about Gatlab.jl, symbolic computing with GATS. Stage is yours.
Okay, if you were here for my last talk an hour and a half ago. Did you check the recording? Yes, we are recording. If you were here for my last talk, that was 14 slides, and I was like relaxed and going in a lot of depth. This is 24 slides, and we're going. Okay, so we're doing generalized algebraic theories in Julia, but we're going to start with algebraic theories because those are like the baby cousin of generalized algebraic theories, and I'm sort of going to give an overview of what does it look like to have a library for algebraic theories in Julia. So first, a review of what is an algebraic theory. We start with an algebraic signature. This consists of a set S of sorts, a set F of function symbols, and for each function symbol, an arity. This means lists of sorts. So an element of S star times S is a list of argument sorts and then a return sort. A single sorted algebraic signature is when you just have one sort. So for instance, the signature for a monoid action has two sorts, monoid elements and set elements, and three function symbols, monoid multiplication, monoid identity, and then the action of the monoid on the set. So the arity of the monoid multiplication is MMM. It takes in two monoid elements and produces a monoid element, and then it returns a monoid element. The same for the others. So a context in an algebraic signature is very simple. It's just a list of pairs of label and sort. A term in a context, so notice we're being very specific here. Terms only exist inside contexts. In first order logic, it's traditional to just like throw in an infinite set of variables, but boo, yeah, exactly. So a term is either a variable, and notice that this variable is given by a numerical index into the context, or it's an application of a function symbol to other terms where the types match up. So we have k terms, and they're of the types that are the argument types to the function symbol, and the return type of the function symbol is the right sort. So for instance, back in the monode action algebraic theory, the term that we might informally write as g times h applied to x would formally be this long term. Okay, an equation in this context is a pair of a context. Yeah, in this context, an equation in algebraic theories is a pair of a context and two terms of the same sort in that context. And an algebraic theory just consists of an algebraic signature along with a collection of equations in that signature. So we gave the signature of monoid actions previously, but we had no laws. Laws are given by equations. So you can see here we have context, term 1, term 2. Those are the three parts of an equation. Okay. So algebraic theories. Now what can we do with algebraic theories? Well, I want to start working towards the category theory of algebraic theories. And so what's the relevant conception of a morphism? Well, there are different things. You can think about a morphism between different algebraic theories, but the thing that I want to talk about is morphisms between contexts. So if we have two contexts, then a substitution from the first context to the second context is for each I in 1 to n, a term of sort S sub I, but in the delta context. So for instance, there's a substitution from the context A is a ring. So there's a theory of rings, and there's a substitution from A to B to the empty context given by A maps to 3, B maps to 2, because 3 and 2 are terms in the empty context. They don't mention any variables. And now, why are these called substitutions? Well, they're called substitutions because you can take a term and use the substitution, replacing all of the free variables in that term with the things that you substitute for in the other contexts. So if we take the term AB plus B and apply this substitution, we get 3 times 2 plus 2. Okay, many concepts are algebraic theories. Not all, but many. So semigroup, monoid, group, abelian group, C-sets. C-sets are kind of funny. If like functors out of finitely presented categories to set, you don't normally think of those as algebraic theories, but they're actually multi-sorted algebraic theories. You have a sort for every object in C. Then these are other things that people don't typically think of algebraic theories, but like actions of algebraic things on sets, those are algebraic theories. So semigroup action, monoid action, group action, abelian group action. You can also take a group action of a fixed group, and that's given for each element of the group, you have a unary function symbol. Then you have rig, remutative rig. Ring, commutative ring, that's supposed to be commutative ring. Yeah, no, commutative rig. A rig with a module over it. That's kind of like a rig action. Of course, ring with a module over it. And then you can also do a rational real or complex vector space, which is a single sorted theory with a function symbol for each scalar. And then you could also do a rational real complex algebra, which is a ring, which along with function symbol for each algebra. So it's like tons of different algebraic theories out there. Now, how do we do this in category theory? Well, a Lawvere theory consists of a set S, a category T with finite products, and a product preserving identity on object functor from finset /S op to T. So essentially what this is saying is that we have a category with finite products, and each of those finite, each object of that category is like a finite set that's typed by the sorts. So you can think of an object of this, of T as a context. And that's in fact what we're going to do next. Any algebraic signature induces a Lawvere theory where the objects are contexts and the morphisms are reverse substitutions. And then an algebraic theory, which is given by taking an algebraic signature and adding equations. You take the algebraic theory, the Lawvere theory that you got from the signature, and you quotient it by all the equations. You quotient the Hom sets so that the equations between your substitutions hold. A model of a Lawvere theory is a product preserving functor from T to set. Notice that this slide doesn't have very much on it. That's because category theory is awesome. This is all you need to know about models. But, okay, I'll say a little bit more. Like a model of any of these theories that I'm talking about, like theory of rings, theory of groups, blah, 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 it's exactly a group. And because this product preserving functor, it picks out a set for every sort, and then the substitutions become operations. So there are sort of like elementary like there are like n to 1 substitutions for each function symbol. And this functor tells you how to interpret each of those. Okay, so that's the math. What does it mean to implement all of this on a computer? Well, there are a lot of different pieces. So the first thing is that we need data structures for everything that I've talked about. So you need data structures for signatures, terms, equations, theories, substitutions. If you want to get fancy, I didn't talk about the math of this, but you can talk about functors between theories, which are just functors between Lawvere theories that are product preserving. And also send sorts to sorts. It's important. But also, another thing, so that you need all those data structures, but then like what functions do you have on those data structures? Well, type checking and inference. Even if you only have a finite set of sorts, it's important to figure out, given a term, what sort that's in. You also want to do rewriting. So when you have terms in an algebraic theory, and that algebraic theory has laws, you want to see whether your terms represent are semantically the same in any model. And that can be implemented by rewriting, which if you saw Priya's talk, it's another application of rewriting. Now this is all like stuff that you can do with these data structures. This is a little bit meta. When you implement an algebraic theory on a computer, you want to be able to give a model for that algebraic theory, which consists of types in your programming language and functions in your programming language. And given a term in your theory, you should be able to interpret your term in that model. Then you also want to be able to do like programmatic manipulation of theories. So, some math requires quite large theories, like the theory of a rig category. Okay, that's not an algebraic theory, I'm jumping ahead. But there are like lots of algebraic theories which have tons of operations in them, and you want to be able to systematically work with those. And finally, we love, we're in category theory, we love to think about like models as objects. And what's the natural thing to do? Well, think about like higher level constructors, which can take a model of one theory and produce a model of another theory. And I'll talk about that in a bit. But anyway, so now we're gonna do a lightning fast toy implementation of algebraic theories. So this is gonna be Julia. It's gonna be, don't worry if you're not getting everything here. You can come to the Julia tutorial for like more stuff about Julia. But hopefully this shouldn't be too confusing if you've seen a programming language before. So here we have a struct is just like it has fields, and each of those fields has types. So a constructor has a name, it has argument types, and it has a return type. We're using integers to represent the types. An algebraic signature just has a vector of sorts, so it gives names, but we refer to sorts by their index into this vector. And then it has a vector of constructors. A vector is list in this context. And then a context is just a list of tuples of symbols and int, where int is a sort. This should refer to a sort, just as before. And then a term is either a variable or an application of head. This int refers to an index in this constructor list. So with this, we can implement type checking. We type check a term in a context because terms exist in contexts. And it's a pretty simple recursive algorithm. Basically, if it's a variable, well, we know the types of all of the variables because those show up in our context. If it's an application, then first we type check all of the arguments to that application, and then we look up the head. We make sure that the types for that constructor match the types of the arguments, and then we return the return type of that constructor. So now let's go to theories. So in this, we can just write, the math translates pretty directly. A equation is, well, a sort. Oh, this is wrong. It should be, we should also have context in equation. This is toy code. Because terms only make sense in contexts. So yeah, so there should be another field here, which is a context. But anyway, an algebraic theory then is just a signature and a collection of equations, and a substitution is two contexts and then a vector of terms, one term for every variable in the domain context. Yes?
You have a if you have, oh, this is cool. If you have a context in the equation, what's the sort for?
The sort is just to say, like, what the types of the left-hand side and right-hand side. I guess you could just infer that. Yeah.
Sure.
So anyway, example, the signature of a monoid has one sort and then two constructors, multiplication and identity. And then the theory of a monoid has the signature of a monoid. Oh yeah, look, I even forgot that this was sort, so I put the context in there. But this, yeah, the signature of the equation with, three variables, all of type the one sort, and then this convoluted way of writing out the actual data structure for these terms. I'm not going to get too far into that. Okay, so that was all the data structures. But now what is a model? Well, the way we're going to work with models is via multiple dispatch in Julia, which basically allows you to overload functions on data types. So we're going to attach all of the functions that need to be implemented for a model to a model struct, which is going to be a subtype of model. And the functions that we're going to define are getTheory, which just returns the theory that that model is supposed to be implementing. Check, which given a sort in your theory, checks whether X is like supposed to be a valid element of that sort according to the model. And finally, app, which actually implements each of the functions. And now, given this, we can oops. given that, we can write this function interpret, which takes a term in a context, and we give the values for each of the variables in the context. And now we interpret the term. The way we do that is that if it's a variable, well, we just look that variable up in the context. And if it's an application of a function symbol to arguments, first we interpret all of the arguments, then we apply the implementation of the function symbol for our model to the values that we've computed for all of the arguments. Okay, example, the monoid of integers. So we have what we call a zero field struct. So this struct has no data in it. Its only purpose is to guide function overloading. And here we have get theory returns theory monoid. Check if there's only one sort. So if the sort is 1, then we just check if x is an integer. And finally, app here, if f is 1, which is the code for multiplication, then we return the first argument plus the second argument. Otherwise, if f is 2, which is the code for the identity, we return 0. Okay, so that was our lightning fast implementation of algebraic theories in 20 minutes. And now we're going to talk about what Gatlab is actually about, which is generalized algebraic theories. So why do we care about generalized algebraic theories? Well, the reason is that there's no algebraic theories for categories. And categories is in the name of this conference. So we gotta have categories. So generalized algebraic theories are like algebraic theories, but with dependent types. So specifically in the theory for categories, the type of morphisms, Hom AB, depends on 2 values of type ob. And why do we need dependent types? Well, it's because composition is only defined when the codomain and domain of your morphisms match up. So that's what this rule says, that compose FG is a morphism only when F is a morphism from A to B and G is a morphism from B to C. So the core of Gatlab has been around since like 2018, has always been an implementation of GATS. This was one of the first things written in Gatlab. But there's been some things that have stopped GATS from reaching their true potential. So Gatlab is a refactor which started this spring to sort of rethink the ways that we use GATS in Gatlab and really do some really powerful generic computer algebra. So what's new in Gatlab? Well, as was in the implementation of algebraic theories, we use de Bruijn levels, i.e. integers, to refer to constructors, variables, and sorts. And the reason we do, in previous Gatlab, we used symbols for this. But when you do symbols, well, things can get messed up because sometimes, you use A in one place and A in another place, and they're actually different A's, but if they accidentally get put into the same place, they can get confused. So if you just use integers consistently everywhere, then you will have correctness of substitution and manipulation. Second is that this wasn't something that I mentioned in algebraic theories because I didn't have time, but we actually implement functors between theories and pushouts of theories, which for multiple inheritance, which I'm going to talk about in a bit. Secondly, I talked about substitutions before. In Gatlab, substitutions weren't quite a first-class construct, but in Gatlab they are. In Gatlab, a model used to be very implicit. You just had a bunch of types around that happened to have some methods defined, but now models are attached to structs, which allow us to do higher level constructions. And then finally, we have a very advanced rewriting system. So I'm going to get more into the last 4 of these very quickly. So multiple inheritance, I talked about rig categories before. We can now define the theory of rig categories by saying, well, it's a monoidal like take categories, put 2 monoidal structures on them, then put a distributive law, which is given by this push out. You take the theory of categories, which has like an inclusion functor into the theory of strict monoidal categories. Then you take the push out, you get a pre-rig category because it doesn't have distributivity yet. And then you add in distributivity to get actual rigs. First class substitutions. Substitutions are really interesting because you can think of substitutions as like symbolic functions. A substitution from context gamma to context delta allows you to take an assignment of values to all of the variables in context delta and pull them back to assignment of values to variables in context gamma. So in that way, a substitution is like a symbolic function. And we can use this to make symbolic lenses. So this is a symbolic lens that implements the open system of the SIRV epidemiological model. We can also do I've been hyping this up the whole time. Higher level module constructions. What does this, model constructions, what does this mean? Well, it means that if we have a model of a category and an object in that category, we can automatically make a model for the slice category over that object. I'm not going to go into this code so much, but you can see basically there's a model of the theory of categories that has where the objects are slice ob, i.e. an object and a hom, and the morphisms are morphisms for any and parameterized by a category and an object that we're slicing over. And then we can define like the check methods for ob and hom, and then the methods for ID and compose on top of this. And a similar construction, though much more involved, could take any Cartesian category and produce the category of lenses for that Cartesian category. And even better, the symmetric, you could do the whole thing with, the symmetric monoidal category of lenses. And then finally, is this the last slide? Yes, okay, excellent. This last slide, egraphs. An egraph records equality of terms. So in this case, I'm making an extension of the theory of categories that just throws a couple null-array term constructors in it. And I can make an egraph and then add this term f compose g to the egraph. Now this term type checks because the codomain of f and the domain of g are both y. But if I try to add g compose f, that fails because x and z are different. But now, if I merge in the egraph, if I record in the egraph that x and z are equal, then g compose f will type check. So this allows you to work with equalities. And then there's all sorts of other stuff that you can do with this. Like you can use this for rewriting where you merge together, you like look for the left-hand side of a rewrite rule and you merge it with the right-hand side. But we are done. So I've done a lot of stuff on GATLAB. Right now the focus is, well, we don't want to have 2 GAT implementations hanging around where one is deprecated. So there's just a lot of work to say, okay, well now we actually have to do like the Indiana Jones swap where we take like the golden idol and swap it with a bag of sand, though maybe GATLAB is the golden idol, I hope. And so there's lots of stuff to do, but yeah, thank you, that's the end.
I would say we have time for one quick question. Also in the Zoom. Well, I'll ask a question if.
Okay.
Okay. I wanted to know how, like, probably the least expected question given the audience, but how do you do in terms of performance? Like, you know.
Okay, this is a great question. The answer currently is the long-term answer is that part of the impetus for developing Gatlab is that in current Gatlab we try to use the Julia dispatch system very cleverly in order so that Julia knows how to compile our functions. But that's kind of awkward because we have lots of logic, and just sort of shoehorning it into the Julia dispatch system doesn't work very well. So part of the idea of Gatlab is say, okay, forget all of that. We're going to be completely dynamic types. If we want type checking, we write it ourselves. And then after we've done all of our computer algebra, we end up with like our term, we end up with an E-graph. And then we compile that into
And you will do it.
Well, we have our own E-graph implementation, which I read the source code of anyways. But we compile it to like Julia code, and then use the Julia compiler to compile that Julia code. And then that Julia code is just like completely specialized. So the compiler can see all of the optimizations and make that go fast. So the idea is that you have your high-level stuff, you work with that very dynamically, and then at the end, you take your terms and you compile them into Julia that is then very fast.
Okay.
Yeah.
Thank you very much. Let's thank the speaker again. And now we should have a tutorial by David J. Myers about lenses.
I want to thank David Jazz. We had a last-minute swap of tutorial presenter, and David. No. Like David Jazz is presenting. There's not a last-minute swap away from him. There's a last-minute swap to him, and he stepped up and made this tutorial. And I'm sure it was a lot of work. So thanks, David.
Or should I, or do you?
So I should probably stop this share.
Yeah.